I'm going to be reading the next part of this book while sitting in an airport waiting to see whether we will get on board a flight on which we are on standby. What Lifshitz and Kalatnikov did was to study models of the universe which were roughly like Friedman's models, but which took account of the irregularities and random velocities of galaxies in the real universe. They showed that such models could begin with the Big Bang, even though the galaxies were no longer moving directly away from each other. But they claimed that this was still only possible in certain exceptional models in which the galaxies were all moving in just the right way. They argued that since there seemed to be infinitely more Friedman-like models without a Big Bang singularity than there were with one, we should conclude that it was very unlikely that there had been a Big Bang. They later realized, however, that there was a much more general class of Friedman-like models which did have singularities and in which the galaxies did not have to be moving in any special way. They therefore withdrew their claim in 1970. That the claim, I think, refers to the fact that there was no Big Bang, right? So, the work of Lifshitz and Kalatnikov was valuable because it showed that the universe could have had a singularity, a Big Bang, if the general theory of relativity was correct. However, it did not resolve the crucial question: does general relativity predict that a universe should have the Big Bang, a beginning of time? The answer to this came out of a completely different approach started by a British physicist, Roger Penrose, in 1965. He used the way light cones behave in general relativity and the fact that gravity is always attractive to show that a star that collapses under its own gravity is trapped in a region whose boundary eventually shrinks to zero size. This means that all the matter in the star will be compressed into a region of zero volume, so the density of matter and curvature of space-time become infinite. In other words, one has a singularity contained within a region of space-time known as a black hole. At first sight, Penrose's result didn't have anything to say about the question of whether there was a Big Bang singularity in the past. However, at the time that Penrose produced this theorem, I was a research student desperately looking for a problem which to complete my PhD thesis. I realized that if one reversed the direction of time in Penrose's theorem so that the collapse became an expansion, the conditions of his theorem would still hold provided the universe were roughly like a Friedman model on large scales at the present time. Penrose's theorem had shown that any collapsing star must end in a singularity. The time reverse argument showed that any Friedman-like expanding universe must have begun with a singularity. For technical reasons, Penrose's theorem required that the universe be infinite in space. So I could use it to prove that there should be a singularity only if the universe is expanding fast enough to avoid collapsing again, because only that Friedman model was infinite in space. During the next few years, I developed mathematical techniques to remove this and other technical conditions from the theorems that proved that singularities must occur. The final result was a joint paper by Penrose and myself in 1970, which proved that there must have been a Big Bang singularity provided only that general relativity is correct and that the universe contains as much matter as we observe. There was a lot of opposition to our work, partly from the Russians who followed the party line laid down by Lifshitz and Kalatnikov, and partly from people who felt that the whole idea of singularities was repugnant and spoiled the beauty of Einstein's theory. However, one really cannot argue with the mathematical theorem. So it is now generally accepted the universe must have a beginning. End of this chapter.